Good morning. So we are in the fourth seminar on our quantum computing series. And on this seminar, we're going to focus more on some of the graph neural network as well as graph algorithm aspects of quantum computing. With graphs, you have that combinatorial complexity where you can, the number of paths in a graph greatly outstrips the number of nodes pretty quickly, or even mediately connected graphs. So with that, quantum really lends itself to these types of problems. And it's one of those things where if you think about it, most of our real world problems typically are kind of graph problems. Transportation, social networks, and even abstract things like knowledge graphs that are really coming into play on how we describe our world around us. So a couple basics about how a normal GNN works. All right, with a normal GNN, we're going to use some kind of kernel or method to embed our nodes into a space. And then we're going to conduct usually convolution on that to simplify that down. Okay, to recreate that and to make our predictions. With these graph neural networks, you'll see edge features, node features, as well as graph structural level predictions. So sometimes, hey, we're trying to predict what this edge is, what this node is, and sometimes what does this entire graph represent. Additionally, like the applications set it, social media, and there's even problems that you wouldn't normally think of as a graph, but that you can implement to display it as such. Okay, it's one of those things. If it doesn't fit neatly in a table, it's probably a graph. Quantum parallelism for graphs. With graphs, you have that combinatorial complexity. How many paths can you find from a graph? How many subgraphs exist in a graph? Where for an item with 100 nodes, it may number it in the hundreds of thousands or millions on how many possible combinations there are. It'd be really nice if we had a way to represent millions of representations at once. We have quantum superposition for that, where we can represent our information by encoding it into a quantum space. We can place these items in superposition, and either through phase rotations or amplitude, we can increase the probability of observing our desired object. So we have some kind of oracle or phase rotation device that basically places in superposition and it identifies the exact thing we're looking for within our data. Fast adjacency matrix computation. There are so many aspects of optimization, machine learning, where mathematicians 50 years ago solved the most efficient way to do this. Okay, if you can get the inverse of a matrix for any quadratic problem, you can solve it in one step, O of 1. The problem is inverting a matrix is so expensive. Okay, now doing it by hand with 4, it's 2 steps, but even whenever you get to a 4x4 graph, all of a sudden now you're doing, 30 computations. It just grows exponentially like that. Matrix inversion is so expensive, but with quantum, we're able to do these very, very fast. Additionally, there's single value or singular value decomposition, SVD, that in 2018 they came out with a quantum algorithm for. So I'm really excited about that, which is another super expensive matrix operation. Like I said before, mathematicians have looked at this and solved these problems. Hey, if you can do this, you've got it. Problem is, up to now, it's just been too expensive to calculate those with a classic computer. All right, and then a lot of the problems that we look at graphs is the shortest path, the most optimal path through a network. Amazon, as quantum increases in the number of qubits it has, I'm sure Amazon's gonna be greatly interested in this because they spend a lot of money trying to find optimal trunk routes. Later on, I made a toy example about disaster relief operations. Okay, through the knowledge of crowds, we're pretty good about things settle into the most efficient thing on like trying to disperse things. But whenever you have a disruption, you have a storm or a natural emergency or something like that, that all gets thrown in disarray. And it takes time for these systems to find the optimal path. It'd be great if we could solve how do we get resources to people in the most efficient way possible quickly. All right, so quantum graph neural network. And I know I've been beating this over the hammer the last several sessions. But right now we're in that NISQ era. We don't have enough qubits. The quantum computers are still noisy And they still have error rates that we have to account for. We have to provide error correction qubits and all this information. So with that, we are going to want to have hybrid algorithms. We're going to allow quantum to do what it does best and send everything else to classical computers. Now with graph neural networks, we're able to assign it these most difficult, most time-intensive aspects of the problem. Okay, whether that's, finding the optimal paths through a network, whether it's those matrix, either decompositions, inversions, is that we can hand that aspect off, and then we can use that as input as some layer of our graph neural network. So if we can do a matrix inversion, or if we can identify the nodes in a network, let's say that the ports that are most capable of providing relief to an area, we can then pass that to the graph neural network for it to finish the processing. And so we're able to balance what is quantum best at, what is classical best at. And I'm going to keep hitting this, that there's some things that even if we had a perfect quantum computer, it wouldn't be better than a classical computer. Okay, there's some aspects like that. Data processing, transmission is never going to be superior in terms of time. So even with a perfect quantum computer, we won't do everything on quantum.
On the GNN aspect, dynamic GNN, which is temporal GNN, or special relationship in the GNN side. So the major issue is the adaptation of the model because of changing of the network side. So adding of the new node, or adding of edge, when the graph is maybe disappear or joining together. From that aspect,
That's
what do you think?
That's quantum's going to have a great role to play here. If you have
I made a wrong. We can do this. There we go. Thank you.
So with that, all right, that's another aspect where there's so many dynamic GNN systems that aren't feasible right now because of the difficulty of calculating either this graph kernel, the optimal paths. We have to accept either random heuristic methods because it's not possible to compute. And so that's going to limit the efficacy of GNNs. But with quantum, provided you have access to a quantum computer within the time frame that you need for your dynamic GNN, the speed that quantum provides is just massive. I was talking to people earlier and showing the graph, and I'll get to it here in a bit, but like a lot of times you're dealing with quadratic speed up from, O of n to O of square root of n. And many of the problems, you're going from O of n squared or O of n cubed to less than n, or n log n. So, going from n squared to n log n is a huge difference. That's going to make that difference for those dynamic models, that if we can send something and get back a result quickly enough, we can constantly update and adapt to those changing graphs.
They have like a local optimization, versus global optimization. For example, I have a multiple GNN and has their own dynamics.
Yeah.
And we also think about the global dynamic, consider about all the GNN side. So from distributed computing, quantum actually doing multiple quantum.
Yeah. No, and it's going to be very task specific with them. It may be that your distributed computing at each, endpoint of your network, they only have small requests and they all send it to a quantum computer. Or it might be kind of like a lot of these distributed networks now, where a central node or through some kind of voting mechanism, they elevate things to a quantum computer and that drops back down.
Like federated learning.
Yeah.
System.
So another aspect and stuff that we can use these quantum computer for with graph neural networks is this is a simplified example, but we have a nearly fully connected graph that we're starting with. And a lot of time, let's say we're searching for a ring, a cycle type graph. The speed at which the quantum computer is able to search those possible graph spaces. Because, for any graph, you have about half n squared number of possible edges. So you have, that factorial number of types of graphs. There's I want to think 32 graphs on 5 nodes and 1 billion on 11. The speed at which that elevates, but with that superposition being able to search all these spaces at the same time, we can really quickly identify structures that we're looking for. So it's that was really interesting, and I understand that this graph is or this chart's a little bit by infidelity. They mean the amount of error they're experiencing. Okay, so the amount of error they're experiencing within 400, 500 epochs of testing this, and you see that even by 100 epochs in, we're at less than 10 to the negative 4. So just the speed at which quantum computer can search these massive search spaces is really intriguing. All right, I'm going to touch on some of the quantum algorithms for graph processing. So a lot of us, if we've touched graph neural networks, graph type problems, we've seen things like random walks, where we don't have time to search the entire space. So instead, we pick a point, we walk k steps, 2 steps, 3 steps, 4 steps, 5 steps to explore the graph space. There's a quantum version of this, but once again, we get to work with superposition. So instead of picking one specific node and going to a neighboring node, we're conducting this walk from all the nodes at once, from all the spaces at once. And so in a way, we're taking something where we were doing a sampling approach and actually doing global assessment on this. And also at a faster or more efficient time step than these random methods. Grover's search for graph. All right, you're going to see Grover's search everywhere. Grover's is really amazing on how it's able to identify whatever your oracle specifies we're looking for. And so if we can specify what we're looking for, we can apply Grover's search within many of our graph algorithms. I have an example here at the end, and I use Grover's search in that. I use a quantum walk and Grover's search to identify which nodes are most important in my graph. And then the quantum Fourier transform, it's a variation on the discrete Fourier transform. It's a graph Fourier transform. We've adapted that to quantum, where we can take these discrete elements and represent them as a signal, whereby we can decompose that signal and identify what's contributing to the effects we see. All right, here's the little practice example I put together. Now, don't get me wrong, this is a bit of a toy example, but it's based on real world information. I took the Maldives, which is an archipelago south of India, and it has many, many, many islands. And I selected 6 of the largest ports as distribution centers. I had information on their population. Now, for my case, to save on qubits, I took that population and I scaled it to 3 bits. So a population of 50,000 was 8, and a population of 25,000 was 4. So I scaled it down to 8 bits just to save on computation. But at the same time, so I have the capacity of the ports, I have the demand for the population center, I have the distance between the islands. And so I was able to create a graph like this, where I have those representations. I have weights on my edges, I have 2 features on each of my nodes. I'm able to represent a problem. And then I'm able to simulate, let's say a typhoon hits the largest port, Male, and reduces its capacity by 60, 70, 80%. How can the other ports in the region help support that largest population center? It's like I was talking about earlier, in normal times, things adjust appropriately. The biggest port is Male because it has the biggest population, it has the biggest demand for its populace there. What happens if that port gets wiped out? It takes us a while to figure out how to most efficiently get those supplies and stuff to the people in the largest city. So, there's a few steps we have to take here. We have to take our graph and encode these node features and these connections with quantum bits, with qubits. After that, we need to conduct our quantum walk. And part of that quantum walk is we're going to have a coin operator. And what the coin operator is just like what it sounds like flipping a coin on which search direction we take. We're going to have a coin operator. That's going to be based on the valency of your nodes. How many edges does each node have? All right, on how many qubits it operates. We're also gonna have the shift operator. Now we'll have the coin operator, and remember that we're working in superposition here. So we're flipping a coin to decide which direction to search. But we're also evaluating all those possibilities at the same time. And we're also gonna have a shift operator, which is doing our walk throughout our graph. Where we're exploring, and while we're doing this, we are taking into account those capacities and demands of the various islands as well as the travel times between them. All right, and then we're gonna apply Grover's search algorithm, just like in every other example I've shown you in this course. We're gonna apply Grover's search, where we're going to increase the amplitude of desired things. Okay, so we're gonna increase the amplitude of the ports in the area that are best able to provide support that's needed. All right, and then here, now don't get me wrong, I didn't drag this circuit into existence. I used normal Python coding, and then we were print out what my quantum circuit looks like after doing that. And so this looks more intimidating than it is. All right, but I said, I sat there and I'm like, hey, I want to place these qubits in superposition. I encoded my information from classical information into my qubits. All right, and watch out, it's big Indian. So I spent forever.
How many qubits are you?
So I'm actually only using 5 qubits for a lot of processing. Now I could have parallelized that out with more qubits, but I wanted to keep the number of qubits I'm using as simple as possible.
How about the gate?
Number of gates, I didn't count them, there's a lot. Yes.
Does 5 qubits mean you're only starting from 5 nodes, or can multiple nodes?
No. So here's what I had to do. All right, as I said, this is a simplified example. I selected the 6 largest ports, and I kind of hand waved that from the 6 largest ports, transportation networks exist. It was a toy example. I didn't want to use all my quantum processing time. So I needed So I needed 3 qubits to represent the port capacity, values from 0 to 8. I needed 2 qubits to represent my coin. Now, I'm able to. I didn't come up with that. That's only 5 qubits. My original plan was larger because I was using other qubits to provide error correction. I was using other qubits to represent other data. But luckily, Qiskit takes a look at it and like, oh, hey, we can collapse this. You don't need 8 qubits, you only need 5. And that's one of the great things about Qiskit and CHASM, these IBM tools that they provide to you, is they're going to take a look at your gates and stuff, and they're going to make it as optimized as possible.
So this is a big step to complete the project. This is an important step, right?
Yes,
Big
yes,
step, But
yes.
how much effort is required?
Effort required and
Time stays for your time.
Oh, my time?
Yeah.
This took me about 7 hours,
7 hours.
but I had to teach myself a lot of things.
Yeah.
I had to teach myself how to implement the quantum walk. I had to teach myself that whenever you program in Qiskit, it's big Indian. Okay, goes this way, not this way like you used to. And so there's things like that, and then there's the normal error correcting. Why isn't this working? Oh wait, this library is deprecated. Those things, but honestly, the first time I implemented a graph algorithm on a quantum computer, it taking 7 hours. I don't think that's bad. It's and there's a lot of tools out there. Unfortunately, the example space is kind of limited at the moment. So you're gonna have to bring up a function and read the documentation a lot of times. That's where you're at right now. You'll have to sit there and play around with it. IBM has lots of notes. Finding where those notes are and how to do things is the tricky part. This library is deprecated. What do they replace it with? They'll have a release somewhere, but you'll have to look, okay, when was it deprecated? All right. So it was deprecated at 0.40. That is released. You're gonna have to look for release notes for 0.40. Okay. It went from multi-controlled topically to control or multi-controlled X. So it's but so that's the aspect. And it's just like any library and stuff. There's a lot out there. You can go as deep into the circuit quantum physics side as you want. You can go a long ways without learning a lot of the quantum physics, quantum circuit side. Yeah, and these algorithms are defined. You know, I didn't make up the quantum walk or the Grover search algorithm. There's people who've implemented it. Now, maybe you'll have to do the translation from someone that's saying, hey, you apply a control not gate to this qubit, you'll have to implement that in Qiskit, where you know, create your qubit, you can apply your control not to it with the CX, you know, you'll have to know that it's CX. Other people have done this work. Other people have laid the groundwork for you to implement quantum, even if you don't have a deep understanding of how quantum circuits or quantum physics works. You know, honestly, like I know the big picture and stuff, but I'd be hard pressed to actually develop like user level software. I focus so much on AI and the math and stuff. Someone said, build me a web page. I'd get there, but I don't know where to start. You know, and it's you can, but at the same time, people lay the ground. If I want to build a website, I'm sure I can figure it out in a day. You know, it's people have done the same for quantum. Time efficiency. I almost didn't want to include this time efficiency graph because it's hard to see what's going on. To conduct the same level of search with a quantum walk, we're talking about over linear time. It's like, you know, it's supposedly linear, but it comes out to like to the 1.1, to the 1.01 or something like that. So you see that increasing thing. The quantum time is this red line all the way at the bottom. It's so much faster. Whenever you're talking about that quadratic speed up, you know, at a, you know, let's say when you're dealing with 100 nodes, it's 10 times faster. But when you're dealing with like 10,000 nodes, it's 10,000 times faster. I'm sorry, at 1,000,000 nodes, it's 10,000 times faster. So it's just such a huge speed up with these quantum walk algorithms. We're able to use that superposition and entanglement to simultaneously evaluate the search space. This looks so great on my home computer screen, but so this is my simplified distribution network for the Maldives. Here we have our main port, which normally has a demand of 204. Okay, and I'm saying the port got wiped out in typhoon. All right, it's not receiving material anymore. Through various airfields and stuff, it can receive materials from other places that are able to accept international shipping. And so what we see here is, and I understand this is a simplified example you could do on a classical computer, but you could easily scale this up to a much larger data set. All right, and what it's done here is it has created these distributions of what islands, what ports, but both by the combination of their demand, their capacity, and their distance from Maldives, how much they should provide. Let me make sure I provided. Oh, shoot. And what it does though is it creates a probability distribution of all the nodes in the network. I meant to include that graph in this, but so what it does, it creates a probability distribution with all the nodes in the network. And you'll see that the nodes with the most demand, or I'm sorry, with the most excess capacity that are in the closest distance are increasing their probability.
Sorry.
Yes, sir.
So this graph, what is the background of this graph? This one.
The right or the left?
Well, both actually. Let's.
Okay, yeah. So the right, so my sample problem was I selected the Maldives, I selected the 6 largest ports. I got their capacities and their populations.
So it's port, right?
Yes, sir.
So it's what kind of problem?
So what I'm trying to model here is like disaster relief. The Maldives is an archipelago. It has various different ports in it. But what happens if, let's say, the largest international port gets wiped out? How is the rest of the archipelago able to support that population in the largest population center?
So so multiple cities, right? One port. Also, I see you're saying maybe.
Yeah, here, let me.
So there's a one port is one now.
Yes, sir.
Then there is it a traveling salesman or sort of?
Yeah, so it's kind of a traveling salesman, it's a route optimization problem. So how much capacity from other ports throughout the archipelago should be diverted to that port, and how is that most efficiently done?
Okay, so is it yeah. A particle name for trying to. Yeah, there's a name for it, that's why I'm.
Yeah, it's kind of a network flow problem, I mean,
Yeah.
I didn't start from like, let's come up with a mathematical problem and
Yeah.
apply it to the situation. I was like, how could I model some kind of real world scenario, and I came up with this. So I wanted to select, you know, what's the most efficient way to provide support to this. You know, the largest city with the largest port, but that port's been wiped out. How do we get supplies into that area?
If you change the reference point to some other island.
Mm.
port,
Yeah,
probably
and
will
I
change.
played with that a little bit, you know, I can increase capacities, reduce capacities, hey, 3 of these, you know, ports were reduced in capacity. And it does change the distribution of which nodes are best able to provide support to those areas. And it increases that probability distribution, and I didn't do it in this example, but then I could take that information where I have a probability distribution of the nodes. I could pass that to a graph neural network.
Yeah.
For more fine-tuned processing.
So what are the features? So the population is one.
Yes.
The resource availability.
Yeah, so I use port capacity. Demand from the population center surrounding that port, and then also the distance. And travel time between ports.
So is this, there's some paper about it problem, right?
Probably, I
How do you
don't.
find this problem?
I made it up.
I'm gonna say- Okay, this is a very typical, supply chain problem.
Yeah, yeah.
So my friend and colleague, Professor Hadley at UMSL.
Yeah.
Studies extensively, he and I are talking about. Speed up.
Yeah.
Yeah, so this is very example, I'm talking more about it, because we're looking for like class project right now.
Okay. Yeah, I'd be happy to share with you, but you know,
So you have code and everything, or
Yeah.
like description, okay,
yeah, it's all on the GitHub,
yeah,
Oh.
okay.
it's all on the
Okay.
GitHub.
Yeah, go back to your curve, because.
Oh, yes, yes,
Yes.
If
So
you,
the
if you,
decreasing is what?
if you change this problem to the saving of the people, like maximizing of the saving of the lives.
Yeah.
kind of thing, there is a relate to this problem.
yeah,
Maybe
yeah,
this is-
that was the motivation behind this, I'm like, you know, what's a real world application where. Optimization transport's not just like, let's make Amazon more money, which I mean,
Yeah.
if you're Amazon, that's great. But like, actually, like, no, people in this area won't have enough water, won't have enough food,
Mhm.
unless we can optimize this transport network.
How about escaping from the area, is that relate from what different?
Yeah, I could see, it'd be kind of like my problem in reverse. Instead of trying to get flows into an area, flows out of an area.
Maybe different.
Yeah. Yeah. You know, and with that, I'd probably like. I would probably. So I would still keep population on the nodes, but I would have capacity on the edges. Hey, how many people can we fit on a boat or an airplane to these various regions?
So you have a decreasing tendency in, means.
Yeah. And sorry, everyone, I'm gonna show him this graph because the color's not showing up well on the projector, but we can pass this around. Yeah. So Male here. is the main port that I said got wiped out in the highest population center. And you can see this color scaling of the capability to quickly provide support. And of course, the nearest ones are green, but there's also some that are surprising based on their excess
Oh,
capacity.
actually here means path, right?
Yes,
Okay,
yes.
okay, I see, okay, okay.
Does that make sense?
Yeah, okay.
Okay.
I get it now. So then what is the bottom, this one, yes?
I was showing the time complexity against a similar classical algorithm versus the quantum.
So the
search.
blue is, yeah,
Classical,
the blue classical, right?
yeah,
So as a number of nodes increase,
yes.
the classical
Yeah.
taking more time.
Yeah, the classical takes far more time as the number of nodes increase compared to quantum, this red line down here.
So this is based on simulation, right? I mean, the quantum simulator.
Yes, and I was able to project this. I took a few measurements
Yeah.
on quantum at increasing node levels. And I projected it out and I did the same for the class.
So particularly for this one,
Mm.
actually quantum computing, I mean, optimization has benefit,
Oh, yes,
advantage, yeah.
yes. Yeah, and it's, that's what we're seeing is,
Yeah.
you know, as I've said, you're never going to want to, you know, render your video game with a quantum computer. It doesn't make sense, not any faster than a classical
Yeah.
computer. But whenever you're dealing with large search space, trying to evaluate, you know, what's the best combination of 5 continuous variables. You know, that's where quantum's going to have the capability to really shine.
Mostly for combinatorial optimization, it is very good.
Yes.
Like this one, for solving any, dense linear algebra. Yeah, you'll get that advantage.
Yeah, it's gonna depend. I mean, there's the matrix operations that is so much better on. You know, in 2018, they came out with the single value decomposition with quantum that's so much faster than in class computers, so it really does. It might not. There are some aspects that I suspect,
Yeah. There are some people that talk about the so-called sweet spots,
yes,
where currently just using simulation, the quantum can actually do it.
Yeah.
Or comparable.
any other questions on this example?
On the example, we are doing cancer research,
Mhm.
and then we are doing abdominal CT scan.
Yes.
Capture about the liver and the kidneys and so forth. And we also are presenting all of this one as the 3D,
Yes.
like graph modeling, and then we also apply that to the cancer, like a cancer spreading, right?
Yes.
Like, starting from liver to the kidney to the some of the aspects in the body of the organ. On that end, we try to find out what's the pattern of the spreading that is following by the zone, the
Yes.
blood vessel or some other pattern.
Right.
So from that angle, if you are able to represent this problem to the graph modeling. and
Yeah, with
this
that
can be-
aspect, I think if you had the knowledge that cancer spreads along blood vessels or along nerves and stuff, so you could represent these as your paths, then you might have quantum applications, but I think that knowledge would have first. I don't know what easy it would be to test all these different various hypotheses.
Yeah.
So
we are looking at some several important biomarker.
Yeah.
And then which are the important value to determine about this cancer, and the progression of the cancer. In different part of the body, right? So this is somehow we are able to combine this to the graph modeling. I think a quantum can give us good feedback about what's possibility pattern, spreading pattern.
yeah, and it's if you can get a valid graph, I think it would help with and you would have a similar to the distribution curve that I had, stuff that you would have a distribution curve of your nodes, and like given your edges, you'd have the probabilities of cancer spreading to this area.
So we can find out the whole of that, and then from which starting point,
Yes.
and what are the possible path we
Yeah.
can go.
And a lot of times too, what they're doing is so we'll use something like the quantum walk and the Grover search. And you'll create probabilities of these various nodes getting cancer.
Yeah.
But that's part of your back propagation loop.
Right.
So, you run that into your graph neural network, it makes predictions, then it runs back and you feed that error into your quantum. They a lot of times will specify certain theta rotations to the input of that. So you can start using that error propagating through your quantum layer to more quickly find that, but that speed up that you get from quickly doing that quantum search of that walk, because of the complexity of searching through nodes in a large graph,
Yes.
that's what quantum is really able to shine at. Yeah, I think that's everything I have.
Do you want to show us about the data?
Oh, yes. So I have on my GitHub. All right, yeah, let me see if I can make light mode. You don't see the screen? All right, go.
There we go. It's done. All right, bear with me, audience, on the screen's not gonna be as bright for you. But at my GitHub, github.com/luke-j-miller/quantum computation series. We have the 4 seminars listed over here, seminar 1, 2, 3, and 4. I have all the code examples. I have the presentation slides as well as the video. I'll have seminar 4's video up there within a week or so. I have all that available there. You can, if we go to this and let's see. All right. All right, and so I run my installation of my necessary libraries. Watch out if you're trying to use a large language model to help you with this. The problem is Qiskit's moving so fast, large language models are trained on deprecated versions. Okay, but use my code and hopefully it'll give you a chance that you want to install syskit.air, not air simulator. So we install our libraries. Has lots to say. All right, we import all our information, or all our libraries. And here's just my data. And as I said, it was a toy example. I took real data, scaled it to 3 bits. Okay, 50,000 is 8, 25,000 is 4. That way I could save on my qubits. I have mappings of the indexes because that way I can reference the qubits directly. So I have, from Male to 000 and back the other way. Remember, Qiskit is big Indian. So item 1 is 100. I have my edge distances as well as the positions for my printing. And this is just more data setup. So we're gonna get through that. Here's a basic graph of the map. All right, and so here we're actually getting into the code. So at first, I have to take all my position qubits and place a Hadamard gate on them to place them into superposition. All right, that way I can begin my search. And then I have my coin qubits via. All right, and I place a Hadamard gate on them as well. So I initialize those positions, and then I have to use my coin operator. That's what does that search, which degree to use. And there's arguments for and against based on the distribution. What I did, since I was working on an irregular graph, that changed because my coin operator has 2 qubits because the biggest number of edges any node had was 3. So that covers from 0 to 3. But if a node only has 1 or 2, then 3 is invalid. So I just moduloed that. But that does change the distribution of how the item works. I could have instantiated a separate coin operator for, 1 through however many qubits, but I chose to make that choice. I still got interesting results, so I stand by it. And so I did this kind of Grover coin operator where I Hadamard and entangle my qubits. All right, and then I do a little bit of math here based on how many coin qubits I have. And then I apply that phase rotation to amplify which edge selection results in the greatest benefit. And then I have to do the shift operator, which is what is conducting those walks from a node along the available edges. And it looks hairier than it is. I entangle qubits. I apply what's called a multi-controlled Toffoli gate, where I have these 2 elements over here. If they're both 1, flip this qubit. If that doesn't exist, don't flip it. And so that allows me, that's my ability to search these for which one has the most resources available. And then I have my demand oracle. Okay, and this is similar to your normal Grover search oracle. And this is what is providing that feedback on which ports have the most capacity within the shortest distance to the ports that have the greatest demand. And so that's applying this multi-controlled phase flip, where I'm adjusting the phase, the rotation of that qubit based on our desired result. And then I execute my code. UC equals demand oracle, I measure. And here, the code I uploaded, I haven't ran through the air simulator. I did test this with running it through IBM Brisbane. That's one of their quantum computers. And that's how I got my time graph. And then I have here's that distribution I was talking about. Okay. So here's that distribution where I have my major ports, Male, Naitharu, all those other ones. And we have the distribution here. That's not the right one. I'll correct this on the GitHub. I results, Male was the lowest. All right, and the other ports were larger. I was running things as I was trying to prepare the presentation. Apparently I changed something, but please believe me. But at the same time, we create a distribution like this where we're able to dictate which ports have the greatest ability, the greatest excess capacity to deliver. Oh, I remember what this is. This is before I reduced Male's capacity. So I ran this where Male has the greatest capacity. That's why it has the greatest excess capacity to provide to others. Whenever I run it, I reduce Male's capacity to 0 because as soon as their port got wiped out, Male dropped down to like 98. And then I have my graph of mapping these capacities. But I just wanted to walk through that code with you real quick. And it's like, you don't have to be, it seems daunting at first. But at the same time, it's kind of like assembling IKEA furniture. Okay, people have solved how to do quantum locks. You can go through and like, okay, I'm going to apply a controlled knot, I'm going to do a phase flip, and IBM is sitting there dying to teach you how to do it. Oh, yes. Okay, so we have several interesting things going on. I wanted to have it ready for this, but I'm dealing with the school and then making sure I have all my I's dotted and my T's crossed. But we are starting a student group. Yes. Yeah, QZ, it's like Mosaic, okay? The Quantum Society for AI and Computation. Okay, we're starting that student group. Along with that is going to come some funding from the school. I'm hoping that we can use some of that funding to bring in speakers, to send us out to competitions or things like that for us to go out to training. Additionally, we're starting an IEEE subchapter focused on quantum computing. Okay, which with that will bring in its own resources. There's a lot of prominent people in the quantum research field in IEEE that we could invite out to provide talks to us. In addition to that, University of Missouri System has recently signed an agreement with IBM that would provide us with increased access to quantum computation. It provides us with quantum programming, and by programming I mean like course programming. So they have 7 courses, 1 undergraduate, 6 graduate courses that they have developed for quantum computing that would give us access to their curricula. It provides us with some access to IBM specifically for questions for implementation. In addition to that, we've recently spoken with Oak Ridge National Laboratory, and they're interested in providing partnership for both using their quantum computation resources on levels that aren't available to you at the normal consumer level. Additionally, they have internships they're announcing soon. And now many of these internships are pathway to employment. jobs. They're not asking for people to fill coffee cups, you know, they're wanting these paths to future scientists at Oak Ridge National Laboratory.
The citizen required.
Not necessarily, internship firms also join there.
My former student, Max Chen,
Yeah.
he's a robotics expert, right? He's looking for quantum computing internship, but in the area of robotics, like part-time.
They do the background checking, takes about 1 month to do that, and then I think like my students, several students get into the internship.
In terms of IBM curriculum, is it a UN curriculum or IBM curriculum?
So what it is there's already a professor at Mizzou,
Okay.
and it's IBM's providing the curriculum, just like a lot of, you know, professors here.
Yeah.
They'll take a Yale curriculum and teach it here, you know, where with their own modifications and tweaks, of course. But hey, this textbook writer who teaches this course presented the information, why would I reinvent the wheel when they did it so well?
Is it credit level, credit based course or just short term?
No. So they have their online coursework that's available to consumers or whoever wants it for free. But they've actually developed, you know, both undergraduate and graduate level, like semester long courses.
I see, okay, credit, okay.
Yeah.
Oh, that's great.
Am I missing anything with?
You may discuss about multidisciplinary.
Oh, yes. And so we're working with discussions with the dean, to provide multidisciplinary courses for quantum computation that is bringing in both the physics, mathematics, computation, engineering. We want this to be multidisciplinary to bring in as many people as possible. That way we can try to get on this quantum bandwagon, that UMKC doesn't get left behind. You're right.
The students get informed if organization is established.
Yes.
Yeah, so maybe they can get emails from you.
Yeah, that would be great. I have my Discord, Dr. Lowe students are hopefully signed in. If it's all right with you, I'll send you an email whenever the course is stood up for anybody who's interested. And it's one of those things where, you know, we're standing up this student group, not that way we can have pizza parties. You know, don't get me wrong, that's a great thing for some student groups and stuff, but I want to bring in great speakers. I want to bring in training and learning opportunities for students here at UMKC for quantum computing.
Okay, we'll start the recording.
All right.